Hi everyone, this is Zhibo Yang. Today I'm going to present our work on how to use inverse reinforcement learning to predict goal-directed human attention. Most computer vision researchers are familiar with salience models that are trained from human gaze data collected during free viewing of images. However, people spend most of their time searching for things with their eyes. As shown in this microwave search example, this visual search behavior is quite different from free viewing. Similarly, if the target is a clock, we can see that salience models cannot predict the human fixations during visual search. So in our work, our goal is to predict the human scan path for categorical visual search, in which subjects are asked to search for an object of a certain category, for example, microwave and clock. To address this problem, we made two major contributions. First, we present a novel, interpretable scan path prediction model. Second, to train this model, we create a large-scale visual search gaze dataset. Up to now, larger-scale gaze datasets for free viewing are available. However, there's no such datasets for standard visual search with more than a few search targets. So we collected larger-scale gaze dataset for visual search under well-controlled conditions. In total, we collected 300,000 fixations from 10 subjects for more than 6,000 images of 18 search targets selected from MS COCO. This makes our dataset an order of magnitude larger than the scale of the existing dataset. Here we show some scan path examples from our dataset. We call our dataset COCO Search 18, and it is now available for download at this link. Just to recap, given the image and the search target, our goal here is to predict the human fixation trajectory, and since we are modeling human gaze behavior, it is important for the model to capture the foveal property in human vision system. In human vision system, we observe a foveated image, which is clear at a fixated location, but is progressively blurred in the periphery. In our method, we model the scan path as a sequence of locations where we choose to deblur the pixels. To approximate human memory effects, we accumulate the deblurrance across fixations. This process can be considered as the sequential decision process, where we have a sequence of states, actions, and rewards. Such decision process can be modeled as a Markov decision process, where the agent is the viewer, environment is the image, actions are the fixated locations, and the states are the foveated images. For computational efficiency, we approximate the foveated image with the high and the low resolution image. In each fixation, we replace the low resolution image with the high resolution pixels at the fixated location. With the foveal approximation, we propose an interpretable state representation, which we call dynamic contextual belief. It is composed of belief maps of every object and background class in the input image, and is constructed by combining the belief maps from the low and high resolution input at all previous fixation locations. Finally, in order to learn the task condition policies that we're looking for, we concatenate the dynamic contextual beliefs with the one-hot task embeddings. Back to our problem formulation. Now we have the states, actions, but what are the rewards? We propose to learn the reward by using inverse reinforcement learning. Our model adopts the popular adversarial training framework with the generator and the discriminator. During training, the generator will generate scan paths with the goal of fooling the discriminator into believing that they come from a person. The discriminator tries to tell which are the human scan paths and assigns them greater rewards. Then the generator will update itself and try to generate more human-like scan paths. This process repeats until convergence. At that point, we will have a scan path that can imitate human gaze behavior. To measure the performance, we use a sequence score and scan path ratio to compute the scan path similarity between the prediction and the ground truth. Our approach is the closest to human oracle and outperforms all the other methods. We also measure the scan path similarity using other metrics. Our model performs the best on all metrics. Here we visualize some of the reward maps recovered by our model. As you can see, high reward is assigned to the laptop when searching for a mouse, and to the monitor when searching for a TV. That's because mouse and the laptop, TV and the monitor are highly correlated objects. This is similar for the car and the stop sign category. We also show that with dynamic contextual belief, our model is highly interpretable. This figure shows the belief map of the refrigerator in the image. By looking at the difference in the action maps with and without that belief map, we can see that people are likely to search at the top of a fridge or microwave because that's where the microwave usually are. So as a summary, first, we created a larger scale gaze dataset for visual search. Second, we present a novel scan path prediction framework using inverse reinforcement learning. Lastly, we propose a novel space representation called dynamic contextual belief. Thank you for listening.